Hello everyone, welcome to this video where we'll dive into the world of binary addition and explore the concept of half adders and full adders. But before we get into the details, let's first understand the basic building blocks behind these circuits, logic gates. In digital logic, the three main logic gates we'll be focusing on are AND, OR, and XOR. Let's break down how they work. So in the AND box, when we have two inputs, we get one only and only both of the inputs are equal to 1, which we can see here. In the OR gate, we get 1 whenever at least one of the two inputs is equal to 1, which is here. And also we have the XOR logic gate, which gives us the output of 1 when only one of the two inputs is equal to 1, which is here. When we add two binary numbers, we end up with two possible outputs for each addition. The sum, which is the result of the addition, and the carry, which is what gets carried over to the next column in cases where the result exceeds 1. For example, when we add 0 to 0, we get 0 and we have no carry out, yes? When we add 0 to 1, we get 1 and we have 0 carry out. When we add 1 and 0, we get 1 and we again have 0 carry out. But when we add 1 to 1, we have 0 and we have 1 as a carry out, which comes here. Okay. Now, if we think about this using logic gates, the sum behaves just like an XOR gate, which we can see here. Because when we add 0 to 0, the sum will be 0. When we add 0 to 1, the sum will be 1. When we add 1 to 0, the sum will be 1. And when we add 1 to 1, the sum is 0, and we have a carry out. Okay, so the carry behaves like an AND gate. An AND gate outputs 1 only if both inputs are 1, which is exactly what happens when we get carry in binary addition, like when 1 plus 1 results in a carry of 1. Yes? In other all cases, we have carry as 0. Okay, so we can summarize that the sum in binary addition corresponds to the output of an XOR gate and the carry corresponds to the output of an AND gate. Now that we understand this, let's talk about the half adder. The half adder circuit is built using an XOR gate and an AND gate. It takes two binary inputs and gives us two outputs, the sum and the carry. The XOR gate produces the sum and the AND gate generates the carry. However, the half adder only works for the first column of binary addition because there is no previous carry to consider. It's perfect for adding 2 bits, but doesn't account for any carry coming from previous bits. Okay, now let's take a look at an example to understand it. When we add the first column, we get 0 as the sum and we have 1 as a carry. On the second column, we get 0 as the sum again, and we have 1 as a carry. Here, we get 0 as the sum, and 1 as a carry. Let's take a look at this addition with the help of the half adder. Okay, in the first column, we have 1, A as a 1, and B as a 1. When we XOR them, we get the sum, which equals to 0, and we get the carry out, which equals to 1. Now let's take a look at the second column. For the second column, our A equals 0, B equals 1, and when we do the calculation, we get the sum, which equals to 1, and the carry out that equals to 0. However, we can see that this is not the correct calculation. And when we look closer, we see that this doesn't count a very important input, which is the carry in. To solve this, let's take a look at something called a full adder. The full adder is an extension of the half adder. It takes 3 inputs, the 2 bits you are adding, plus the carry from the previous column. The full adder uses 2 XOR gates, 2 AND gates, and an OR gate to calculate both the sum and the new carry. With the full adder, we can handle multiple columns of binary numbers, allowing us to add long binary sequences with ease. Take a look at the same example with a full adder. We had 101 and 11. When we add them, we get 0, we carry 1, 0, 1, and we carry 1 again. Okay, so let's go column by column. In the first column, we have A, which is 1, b is also 1, and the carry in is 0. When we XOR them, we get the sum, which equals to 0. Here we have 0. And what do we have next? The carry in is 0, and when we XOR 0 and 0, we get 0. Now we have 0 here and 0 here. When we end 0 and 0, we get 0. And when we ended it here, we had 1. So we get 0 and 1. When we OR 1, 0 and 0, we get 1 as the carry out. So it works for the first column. Now let's pass on to the second column. So in our second example, we have A that is 0, B that is 1, and the carry in that is 1 also. When we XOR 0 and 1, we get the sum, which is 1. And when we end them, we get 0. When we XOR the sum and the carry in from the previous action, we get the sum, which is 0. And when we end them, we get 1. When we OR 1 and 0, we get 1 here. We can see that it works for the second column too. Now let's do the same for the third column. Here we have A is equal to 1, B is equal to 0, and we have a carry in that is equal to 1. The sum we will get 1. Here we have 1. The end we will get 0. Here we have 1 and 1. The end will be 1. 1 and 1. The XOR will be 0. And here we have 0. The carry out will be 1. And finally we get it that it is right for the third column too. And finally, let's take a look at 2 3-bit number addition. How would it happen? So for 2 3-bit numbers, we will have one half adder. There could be even a full adder instead of this half adder, but we can write a half adder as for the first column we do not have any carry in, or we can say that the carry in is 0. Here we have the sum, which equals to the sum of our first column that goes into the memory. And we have the carry out, which is the carry in for the second column, as we know. Here we will have a full adder that will give us the sum of the second column that will again go into the memory. And we will have the carry out of the second column, which becomes a carry in for the third column. Let's write here. Here is the A, and here is the B. This goes into another full adder that gives finally the sum and the carry out that is needed. And let's take a look at one example. So we have 101 plus 011. Here we get 0, we have 1 to carry, 1 plus 1 is 0, 1 to carry, 1 plus 1 equals 0, and 1 to carry. Let's write the memory here. Okay, so on the first, A equals 1, B equals 1, the sum will be 0, the carry out will be 1. On the memory we have 0. Okay, so here we have 0, we have 1. In the full addition, we get the sum equals 0. Here we get it 0, and the carry out equals 1. And for this last column, we have A equals 1, B equals 0, and the carry in, or the carry out of the previous action, as we already know, is here. We get the sum, which equals to 0, and the carry out that equals to 1. Here we get 1, 0, 0, 0, 1, which is 1, 0, 0, 0. Sorry, we got 1, yeah. That's all. Thank you for watching the video. Subscribe if you want.